The purpose of this lab was to estimate the mass of a black hole by analyzing the motion of a nearby star. By computing the star's velocity using differences in position data, we were able to calculate its momentum at each step. Newton's second law, which states that net force is the rate of change of momentum, was applied to determine the total force acting on the star. Assuming that this force is purely gravitational, we used the equation for gravitational force to estimate the black hole's mass. Based on our calculations, the estimated mass of the black hole is consistent with the expected mass of a supermassive black hole. For part 1, the net force in the star was assumed to be solely due to the black hole located at the origin. According to Newton's law of universal gravitation, the gravitational force exerted by the black hole on the star is given by F equals G m1 times m2 over r, where G is the gravitational constant, m1 is the mass of the black hole, m2 is the mass of the star, and r is the distance between the two bodies. This force acts as the net force in the system, dictating the acceleration of the star according to Newton's second law, force equals mass times acceleration. Since the only significant force acting on the star was gravity, we equated this to Newton's law of universal gravitation to solve for the black hole's mass. By observing the star's motion and applying these principles, the black hole's mass was estimated to be 9.51 times 10 to the 33 kg, aligning with the expected range for a supermassive black hole. In part 2, a simulation was conducted of a spaceship attempting to achieve a stable figure-8 orbit around a planet and its moon. The spaceship's velocity and position were numerically updated using the velocity and position update formulas derived from Newton's second law. Given an object's acceleration, its velocity and position at each step are updated where delta t is the time interval used for the simulation. These equations allow for iterative computation of the spaceship's motion based on gravitational forces exerted by the black hole and the planet. The initial velocity of the spaceship was carefully chosen to avoid collisions while maintaining a stable orbit with the values that allowed for a successful figure-8 trajectory, being negative m divided by s and m divided by s in the x and y directions, respectively. The analysis of parallel and perpendicular forces reveals an important distinction between net force and the rate of change of momentum. The net force is the sum of all forces acting on an object, while the rate of change of momentum describes how an object's motion evolves over time. The parallel component of the force contributes to changes in speed, while the perpendicular component only affects direction. In the case of the star orbiting the black hole, the gravitational force is always directed toward the black hole, meaning the force has a perpendicular component that causes the star to curve in its orbit without necessarily speeding up or slowing down. However, if there were an additional force component in the direction of motion, it would cause the star to accelerate or decelerate along its path. This distinction is observable when tracking changes in velocity over time. To predict the motion of the entire system, including the black hole, star, planet, and moon, all gravitational interactions would need to be included in the computational model. The dominant interaction is the gravitational attraction between the black hole and the star, as it exerts the strongest force in the system. However, the star also pulls on the black hole, though its effect is much smaller due to the mass difference. Additionally, the planet and moon experiences forces from both the black hole and the star, while also interacting with each other. These interactions are weaker but still necessary for accurately modeling the full system. By considering only the most significant gravitational forces, the computational model can be simplified while still capturing the essential dynamics of the system. In conclusion, this experiment provided valuable insight into the motion of celestial objects under the influence of gravity. The observation of how net force and its parallel and perpendicular components affect an object's velocity and trajectory over time was key. Additionally, the relationship between the rate of change of momentum and net force demonstrated Newton's second law in action. The model also highlighted how dominant gravitational forces shape the system's overall motion, emphasizing the importance of accurately accounting for all significant forces in astrophysical simulations.